Thank you. So today I'm hoping to start aligning the lectures a little bit better with the slides. So there's no new slides from what we had last week. I'm going to finish today. I'm going to finish with induction. So if I need something to fill in the time, I'll probably talk a little bit about the answers to assignment 1. But we'll just see how we progress, and maybe I'll pad it out with some more induction examples. But so we will start on the next topic after induction, which will be logic, and I'll put the slides up for that as soon as practical, but hopefully well in advance of the next lecture. So just starting with the recap of what we covered last week. On some administrivia. So first of all, the announcement went out last night. The second assignment has now been made available. It's due in 2 weeks' time, Sunday midnight. So give you exactly 2 weeks again. Same rules apply. Lateness penalty of 10% of your raw mark for every 12 hours or part thereof. With a 1 hour grace period at the start, and if you're seeking extension, you need to apply for special consideration. Assignment 1, I think all the applications for special consideration are now in, and I think everyone's submitted, so I can start marking. And as I said, I'll talk about the answers to that if I have some time at the end of today's lecture. There were a couple of loose points last week, notably the one of the unrolling examples, which actually wasn't quite correct. The way I unrolled it was the answer to the quiz, and so I just wanted to clarify that. I did post this on the forums, but just in case people missed it. And the other one was getting the fast Euclidean algorithm, the time bounds for that, which I'll also talk about. Also made available, I've put up another challenge question, again a type that you can submit. So again, it's good. It gives people a chance to actually program, which you don't normally do in this course. Programming is not a component of this course. But it gives you a chance to sort of like tackle a programming challenge, if you like, and it requires some thought about it to actually make it run in some sort of reasonable time. So at the moment, a couple of people have made an attempt at it. I'd like to see a few more. We had quite a few attempts at the first one. This again is a case where you just upload your attempt and it'll spit out the answer. It'll tell you, well, it won't spit out the answer, it'll just tell you how you're doing. And then there's a bonus question attached to the challenge questions, which is not for submission, but it's, again, something to think about if you're finding this material relatively straightforward. Finally, the latest quiz. I just wanted to talk a little bit about the problems on that. People generally found it okay. It was nice to give a lot of examples, a lot of practice with the algorithmic analysis. Algorithmic analysis is something that crops up in all your courses. So when you do programming, you sort of, you'll start to see what it is. So it's something that if it's not the first time you've seen it now, it won't be the last time you see it, certainly in a lot of other courses. And so I treat it more formally than a lot of other courses do, but I think it's useful having the formal definitions to build upon. So first of all, I just want to make some comments about the second assignment. So there's 4 questions. 100 points again. I think it's probably a little bit hard, a little bit more challenging than the first assignment. So, but it's nothing beyond you. But there are some points that often people trip over. So I just wanted to clarify a few things. So the first question here is another example of these proof or disproof. So just give you 5 more things to practice proof or disproofs. So you either have to prove it or give a counterexample. I should mention that relation composition isn't part of the set theory notion, so the proofs probably aren't set theoretical proofs. That's not saying you can't do them that way. I just find it unlikely that you will be able to do it that way. But so it's more a case of going back to the definitions, working through the definitions, and coming up with a result. But basically, so if you're trying to prove something, we're talking about equality of relations, and relations are just sets, so we're talking about equality of sets. So you need to go through and revise or review how you show two sets are equal. Or you need to find counterexamples, and again, you need to review how to prevent a counterexample. So here, S is an arbitrary set, and R1, R2, and R3 are arbitrary relations, arbitrary binary relations on that set. So you can only pick specific relations if you're trying to come up with a counterexample. If you're trying to prove it, you need to prove it for all sets, for all possible relations, R1, R2, R3. Problem 2 then sort of actually builds on problem 1 a little bit, because again we deal with the relational composition, but this is what's known as constructing the transitive closure of a relation. So I'll tell you now that it's called transitive closure. You can go up and look up about it. As always with assignments, I'm assessing your ability to understand and your ability to show how you can build on the standard definitions. So yes, you can go and look up transitive closure and probably find all the proofs to this online. That's not going to help. The whole point of these assignments is to get you used to the idea of the types of questions you're going to get assessed on in the final exam. Right? To get used to what you're going to get assessed on, what I'm looking for when I'm assessing you. Right? So going and finding a shortcut, a simple answer to these questions and answering it in 1 or 2 lines the best you can. 1 or 2 lines using some weird and wonderful trick or some weird and wonderful obscure reference is not demonstrating your ability. It's not going to give you feedback that you're going to be able to take into the exam, because you're not going to be able to access those weird and wonderful resources. So everything that's on this assignment, you should be able to do from just the lecture notes alone. So you should try and get it out yourself so that you can understand, what you don't, or what you do and don't understand, where you're having troubles, where you're having difficulties. Ultimately, an assignment is worth 10%. So this is 100 marks. So each individual mark is 0.1 of your overall grade. Finding a shortcut to solve, 3 or 4 problems is going to count such a small, insignificant part. When you look at the exam, the exam is probably of the order of the same size, same number of questions as here. And so each question is worth 6 times as much on the exam as it is worth here. So keep that in mind. Use the assignments as an opportunity to practice practice for or prepare for the final assessment. So problem 2 is about computing the transitive closure. So in particular, so this is again an arbitrary set S, and we have an arbitrary relation, and we define this sequence of relations in an inductive manner, or a recursive manner, sorry. And then we have some properties. So if there is an I such that this happens, then I want you to show that Rj is equal to Ri for all j greater than or equal to I. So we don't know that there is necessarily such an I, but we just want to show if there is an I, then this property holds. And again, if there is an I, then this property holds. And then C is phrased very much like how we've been doing induction proofs, induction type questions. You don't necessarily have to prove it by induction. Right? There is no requirement to prove things by induction unless explicitly stated. I generally don't like to say that. I like to open up your creativity. You can prove things however you want to. And then for part D, right, so the first part of for part D, E, and F, we make some assumptions about our set S, namely that it has k elements in it. And the first part basically shows that r to the k is equal to rk plus 1. That means that k, the number of elements in S, is such an I for A and B. Right, so k will be a witness for the answer for A and B. Right, and so basically, once you've established D, for E, you can use the fact that k satisfies this, and so therefore, things like that. And so ultimately, we're trying to show that the kth relation in this sequence, how we've defined it, is a transitive relation. Right, so we start with the relation R, we build up a sequence of relations depending on this R, and then the kth relation we're going to get is a transitive relation. And then a nice little cute result. Basically, if we do that same process but with a slightly different relation, namely R union R converse, we actually end up with an equivalence relation. So this is how to take a relation and do some operations to it and actually end up with an equivalence relation. And there are some challenge questions that I can ask on top of this this set. So I might do that when I come around to posing some more challenge questions. So that's question 2. As I said, you may find question 1, the answers to question 1 useful, but you don't have to use them. You may find induction useful, but you don't have to use it. And I leave it at that. Problem 3 is about a inductive definition, and then some so it's an inductive definition of a binary tree, and then some inductive definitions of functions, and then what is known as a structural a proof based on all this structure. And so again, you may want to prove this using structural induction, which we'll talk about today, but again, it's not necessary. The important thing here is that I'm interested in the abstract definition of a binary tree. So the hint here is to look back at the. So this is very similar to a list, except a linked list, except you have 2 successors rather than 1 successor. So I would suggest you go back and have a look at the abstract definition of a linked list. The reason I'm giving lots of hints in this bit because basically B, C, D, and E all depend on A. So if people struggle to get A, then it kind of makes the whole question a little bit hard. So big hint, review the recursive definition of a linked list, particularly the abstract definition of a linked list. One thing I'll say, there's no requirement that we store data in the nodes. So we don't have to store any data. All we care is that a node has 2 successors. It doesn't necessarily have to have data in it as well. So it can be a little bit loose as that. The only thing is, just to make life easier, for the internal function, for an empty tree, to make life easier, say that the number of internal nodes of an empty tree is actually -1. That just makes things look a little bit nicer. So you don't have to take this definition. You can come up with other definitions that don't rely on this definition of it being -1. But I won't object if you say that the number of internal nodes of an empty tree is -1 to make your recursive definitions a little bit nicer. And then problem 4 is an example of a logical specification. We'll talk about logic starting on Wednesday, so we don't need to worry too much about that. But basically, we have a real-world scenario going on here. We have networks that may or may not interfere with one another, and in order to avoid interfering with one another, they can operate on one of 2 channels. And what you want to do is sort of like come up with an algorithmic procedure for deciding if there is an assignment of channels to networks such that everyone can operate without interference. Right, so yes, you can look at this and you can say, yeah, there is. Right? So on this, on this very small example, you can do it almost by trial and error. But what I'm trying to do is trying to get an algorithmic approach to look at it as a big picture. And what we're going to do is we're going to turn it into a problem of determining if a propositional formula can be satisfied. So what I'm trying to do is get this real-world problem. I want you to turn it into a propositional formula such that if the propositional formula is satisfied, the real-world problem has a solution. And if the propositional formula cannot be satisfied, then the real-world problem does not have a solution. Right? So it hopefully it's more or less steps you through it. We'll talk about all the definitions we need here. But an important thing to note is that you get 4 marks for actually carefully defining the propositional variables you're using. Right, so the first step, although it's not listed there, is to carefully define the propositional variables you're using, and then to define phi1 and phi2 and phi3, and then to do some rough calculations. And then this one, so based on your answer to the previous question, so this one, this question here shows that you want to show that phi1, that this thing here is satisfiable. And then, so you do that by showing a truth assignment. So that's all in the realms of logic. And then what I want you to do is take that solution in the realms of logic and turn it into a solution of the real-world problem. So that's what part 2 is doing. Right, so part 1 should be an answer in the realms of logic, but of course that has nothing to do with networks and channels and so on and so forth. So what I want you to do is take that solution from logic and turn it into a solution to this problem here. So that's what B2 is asking. So that's more or less that is the second assignment. As I said, we'll cover the necessary bits for logic at the end of on Wednesday and next week. So some comments from last Wednesday's lecture. So first of all, the quiz question we had to deal with. I inadvertently dismissed a very important thing. So the quiz question was asking about Tn equal to 2Tn minus 2 plus n. And I said, oh, right, so we unroll this. We start unrolling this. We're going to get that this is 4Tn minus 4 plus n plus 2 lots of n minus 2. And I was throwing these away as just order n. But in fact, if you keep unraveling it, we're going to get n plus 2n minus 2 plus 4n minus 4. These things are actually starting to get quite, the coefficients out here are actually starting to get quite big and quite important. So in general, the ith term is 2 to the I t n minus 2I plus, and then we're going to have, basically we have, we have the sum, so I equals 0 to, well, I don't know, let's go j equals 0 to I minus 1 of n minus 2j times 2 to the j. And this thing here, actually, you can't just throw away because this is like you've got a 2 to the power, or to the power something which is getting close to n here, and so you can't just throw this away. In fact, you've got n lots of 2 to the j. So you could conceivably upper bound this. This is going to be upper bounded to be 2 to the n t0 plus n, and then we're going to have n lots of, sum from j equals 0 to n minus 1 of 2 to the n, which is just 2 to the n itself. So we could have an upper bound like this, and then you can't actually say that 2 to the n is the dominating factor, because n times 2 to the n is actually so 2 to the n is in order n to the 2 to the n, but n to the 2 to the n is not in order 2 to the n. Right? So n 2 to the n, O of 2 to the n, is not the same as O of 2 to the n. Sorry, O to n times 2 to the n is not the same as 2 to the n. So this is an example of, if I take an upper bound approximation, simplifying things, I'm actually going to get an answer that's worse than what I want. Because what I can do by carefully analysing this thing here is actually not n times 2 to the n, but if you do some quick calculations, this thing here looks something like 2 to the n minus 1, more or less, when I becomes n. So if you do some quick, careful calculations, you get this, and I might go through proof by induction for that. So as I see over there, what it boils down to, when you do the unrolling, you need to show this actually somewhat subtle result, that the sum of I equals 0 to m of 2 to the I times m minus I is actually order 2 to the m, not just 2 to the m times m. So that in itself is not easy, but I'll leave that there because I'll use it as an example in my proof by induction. The cheating way to solve this is to say, right, let's define a new function, f of n. So what does f of n do? It takes n and multiplies it by 2 and then plugs it into t. Right? So f of n is a well-defined function. It's t of 2n. But we know what t of 2n is. T of 2n is 2 lots of t of 2n minus 2 plus 2n. Right? But t of 2n minus 2, that's just 2 lots of n minus 1. And t of 2 lots of n minus 1 is just f of n minus 1. So we get this result, f of n is 2 lots of fn minus 1 plus 2n. Right? And now we can apply the linear form of the master theorem to get that f of n is, well, it's order 2 to the n. But what was f of n? F of n was t of 2n. So t of 2n is 2 to the n, so therefore t of n is 2 to the n over 2. So this substituting functions is a nice little trick, and that's basically, it is the trick that you use to get the linear form of the master theorem. You choose an appropriate function, and rearrange it, and you'll end up with something like this, where you're making use of the master theorem in there. And I'll put that into, that's in one of the practice questions when I get around to getting them up. Yep. Yes. So we've got an upper bound here. We can also, to get a lower bound, you can say, right, t to the n is this thing here, which is greater than or equal to 2 lots of t to the n minus 2. Right? And then you can unravel it, and you see that t of n is greater than or equal to 2 to the n over 2. Right? And then that gives you a matching lower bound. Alternatively, the unraveling, right, that was the dud step, I should point that out. Without that step, we've got a lot of equalities, and in fact this sum is equal to this thing here is an equality, and so actually everything there will actually end up as, you can actually sort of, when you do the unraveling, it's all theta. But in general, it's, if you do a reasonable job, it's like big O is sufficient, and that's in this week's quiz, or the quiz that was due today, the way I stated it was to say give the best bound for an upper bound, right? So that says that if you work it out to be O of n, and it works out. So if you work out the algorithm to be O of n, right, O of n squared is technically an upper bound, but O of n is a better bound. So that's what I'm looking for. I'm looking for the best upper bound you can get, or the best out of the selection. So in general, I'll try and avoid theta because it gets a little bit messy, particularly when it comes to algorithm analysis. Generally, I want the best upper bound for a big O that you can get. The second point I got stuck on Wednesday was when I was analysing the faster Euclidean algorithm, and it came down to sort of I wanted to show that. So I went from mn. So I was looking at, say, the time complexity of, so I was looking at the time complexity of n, which was the time complexity of m plus n. And so mn, that pair will go to, assuming m is bigger than n, m mod n, right? And so what's the time complexity of this? Well, the time complexity of that was m mod n plus n. And I wanted to bound this here by some multiple of this thing here. So I wanted to say that, so Tn here went to say Tn over, well, this thing here was bounded above by, I said in the slides Tn over 2. Then when I realised I was wrong, I corrected it to Tn over 1.5, which is true, and it's actually quite a nice argument to go through. I posted it on the announcements. But it's something that probably going forward I might just set as an exercise, if not a quiz question, or an assignment question. But basically the proof goes as follows. So it uses the fact that m is equal to m div n times n plus m mod n. Right? That's essentially the definition of mod, right? Because m mod n was equal to m minus this thing here. And so m plus n is equal to m div n times n plus m mod n plus n. And if I divide that by m mod n plus n, right, I have here this bit here over this bit here, so that all gives me 1. And then, so I'm left with m div n times n over m mod n plus n plus 1. And then, well, we had the assumption that m was greater than n. So m div n is greater than 1. So m div n is greater than 1. And m mod n, because it's the remainder of m on division by n, right? We know that that is less than or equal to n. So this thing here, the numerator is greater than or equal to n. The denominator is less than or equal to 2n. So we get that this thing here is greater than or equal to n over 2n plus 1, which is just a half plus 1, or 3 over 2. Right? So rearranging everything, I get that m plus n is bigger than 3 halves of m mod n plus n. So the 1.5 I put in the corrected slides is correct. And so if my input decreases by a factor of 1.5 at every stage, then you can apply the master theorem, and then you get that the running time is log base 1.5 of n. But of course, log of all bases is equal asymptotically, and so we don't. So it's just as good as log n. As I said, quiz 8, people generally did quite well. I think the hardest or the worst performing question was actually the first one, which was interesting. So just a note. you don't need to understand when you're doing algorithmic analysis, you don't actually need to understand what the algorithm is doing. It can help, it can be useful, but in particular, there may be typos. This one was highlighted. Somebody pointed out that, I think incorrectly. So with question 4, there was an issue that if all the elements of the array were the same, then the array wasn't going to terminate. I took the example. I missed the sentence at the start that said assume every element of the array is different. Right? And the same thing happens here as well. You assume every element of the array is different, and that x is an element of the array. I didn't actually I didn't necessarily mention those because it's not important for the analysis of the runtime. So again, you just look at the running time is counting the number of elementary operations. So let's just identify the elementary operations. Oops, I've missed a couple. So there's a comparison here, and a comparison and a array extraction here, and another comparison and array extraction here. So these are so every line is order 1, but I've got nested while loops, which on the face of it looks like it might be sort of n. So while I is less than j, so I and j range between 0 and n. And then, so it looks like I'm doing like, so this while loop executes n times, and then this executes at most n times, and so I get n squared. But in fact, if you think about what's actually going on, the way this program works is basically you have your list, you have I at the start and j at the end, and what you do is you move I up every time you move I up as long as the ith element of the array is less than or equal to x until you basically get to a point which is greater than x, and then you move j down until you get to a point where the jth element is less than x, and then so that's what those two lines do, and then this line here swaps those two elements around. So you can imagine basically what I'm doing is I've got an element x in my array. I'm putting everything that's less than x to the left of it, everything that's greater than x to the right of it, and I'm just basically building it down. And what happens is, well, if you think about it, these lines here, I and j just get closer and closer and closer, and then they meet, and this while loop will exit. And so I increase I decrease j, but they don't cross over. And so this whole while loop here only executes, the interior bit of this only executes or n times, essentially. So the whole algorithm is going to be order n. This is quite a nice, very useful function for various things like quicksort. Just knowing that you can take an array, if you've got a particular element of the array, you can split the array up into everything that's less than that element and everything that's greater than in O of n time. Very useful algorithmically. So that's question. There was one of the other question on the quiz that I did want to talk about quickly was the my function. So I defined a function. So my function n. What did it do? If n was equal to 0, return 1 or something. I can't remember exactly this. Otherwise, return, so else, return 2 times my function of n minus 1. Now, when we do the algorithmic analysis of this, right, I'm not calling my function n minus 1 twice. I'm only calling my function n minus 1 once, taking that result and multiplying it by 2. Right, so if t of n is my running time for my function of n, right, then, well, these steps are O of 1, but they're the base case. The recursive case is I'd make one call on my running time of, one call with n minus 1 as my parameter, and I do a multiplication and I do a return. So my recurrence looks like this. So it doesn't necessarily look like so although I'm doing like 2 multiplications of my function, my recurrence here looks like this. So this is just going to be Tn minus 1 plus O of 1, and this will resolve to T of n being O of n. If, however, my function had been defined not as 2 times my function, but as my function plus my function, now I am doing 2 recursive calls on my function n minus 1. So T of n is not, so it's going to be T of n is going to be 2 lots of T n minus 1 plus an addition, right? And then this will resolve to T of n being order 2 to the n. So when actually writing programs, you should be cognizant of this fact that basically if you're making a recursive call and you make the same recursive call multiple times, you're going to drastically change the running time of your algorithm, right? So just by taking 2 recursive calls doing the same thing, making 2 separate calls, that gives me exponential running time. If I if I recognize this and just said 2 times this, then I get linear running time. And that's the principle behind dynamic programming. It doesn't just extend to like recursive calls of n minus 1, but my function n minus 1 is going to, in its process, call my function n minus 2. And so if this had been return my function n minus 2 plus my function n minus 1, if I'd actually stored the value of n minus 2 when I computed my function n minus 1, I could actually, instead of making a recursive call to get n minus 2, I could actually just pull that value in. Right? So if I save that value in advance, I could do that. Don't need to worry too much about that. That's just looking ahead to other concepts. But the more general, or the specific case listed shown just there, is a good indicator why you should be careful when doing these things. Anyway, just a recap of what we actually did last week. So we finished up on recursion by talking about recursive definitions and solving recurrence equations. And I covered 3 ways of solving recurrence equations. So you have the unwinding method, which will work. The difficulty with the unwinding method is that you need to identify the ith term. So you sort of need to unwind it until you see a pattern, hopefully. There's simplifying the procedure using big O notation. So for instance, you might not unwind very nicely, but if you say, right, let's just assume that everything here, or that t is increasing, so t of n minus 2 is smaller than t of n minus 1. So then I can say t of n minus 1 plus t of n minus 2 is smaller than 2 lots of t n minus 1, and then I know how to solve that recurrence. And so you get a bound. You might not get an optimal bound, but you can get a bound and you can get an answer. Then the final approach was to use the master theorem, which works in a lot of cases, and a lot of cases that are going to come up, but there are some cases where it doesn't work, it doesn't apply. But in some of those cases, they can be resolved with a variation of the master theorem. And then I moved on to the application of all the work up to this point, which is algorithmic analysis. And the main thing about algorithmic analysis is that the general default rules. We're looking at worst case analysis. So we look at the highest cost examples. We're looking at generally we're looking at the running time, which is just the number of elementary operations. I gave an example of squaring, so it's n times n, and I said, oh, this is order 1. There's been a breakthrough paper by some people here in the maths department that they show that multiplication of 2 n-bit numbers can be done in order n log n. So the assumption that it's order 1 is actually, in some sense, belittling that result. It's quite a nice result. It's not really applicable to real-world scenarios because the constants are in the big O of n log n are so large that you might as well just have the well-known order n log n times log of log n algorithm, the one that's been around for a while, algorithm for doing multiplication. But their result is very nice, very famous, very nice established result. But it just basically shows that sometimes looking at the number of elementary operations, or the definition of elementary operations, varies depending on the application you're looking at. But for us, simple arithmetic operations are elementary. Comparisons, accessing memory cells, are all printing a character are all fairly basic elementary operations. And again, we just say, rather than saying like one elementary operation, two elementary operations here, we just say order one, and we start approximating right at the base level. And then we can also use big O to simplify some analysis. So like if we have n plus n squared plus n cubed, we just big O it and get just order n cubed to make things simple. We can use also the upper bounds because we're using worst case analysis to simplify things. And one thing I forgot to mention that is hopefully a little bit apparent is that our aim is to compare or to get an analysis in terms of simple functions. So like I'm looking for order n, I'm looking for order n squared, I'm looking for order n log n. I'm not looking for order 3n squared plus 5, for example. Although technically order 3n squared plus 5 is the same as order n squared. But basically I'm trying to express my running time in terms of very simple monomial functions. So like one term with with a coefficient of 1, generally polynomial type. And then finally, we finished on Wednesday with a quick introduction to basic induction, which I'll expand on today. So just a reminder what the master theorem looks like, just to keep things on track, or to give you something to remember, or to keep in your summary, I guess, your ongoing summary. The master theorem applies to recurrences of this particular form. There's a good question on the forum today. It said, well, what if we had like a lots of tn minus 3 over 5 or something like that? So for those, you can't apply the master theorem, but you could use like the tricks that we talked about, like using upper bounds to get, so t of n minus 3 over 5, assuming t is increasing, right? T of n minus 3 over 5 is bounded above by t of n over 5. And so then you get t of n is bounded above by t n over 5 plus n, and then you can then apply the master theorem. So the master theorem, you can have less than or equal to here and have big O's. You can have, technically I think you can get thetas out here. I don't want to state it with thetas because there's a little bit of playing around. I will mention that there are some conditions here on f that I haven't stated. It doesn't always apply to functions like this, but for all purposes in this course, you can assume that everything is well behaved and behaving nicely. The important thing here is that f is some polynomial times logarithmic factor, right? So it's like basically f of n it looks something like 3n squared times log n, or 3n squared times log n squared, or something like that. And then we have two important parameters, c, which is the polynomial power of f, and d, which is just log base b of a. And then the solution to this recurrence depends on the comparison of c and d. If c is less than d, then it's order n to the d. If c is equal to d, then it's n to the c plus an extra logarithmic factor that we had before. And if c is greater than d, then it's just the same as f of n. So it's just n to the c, effectively, if k was 0. And so some cases where it doesn't apply. So there's the three cases that I highlighted last week. Another one that someone brought to my attention. If we have something like t of n is equal to tn over 2 plus 2 to the n, right? So here fn is not a polynomial. It's an exponential. again, the master theorem won't apply directly here. Well, it can apply, but I don't want to say that it does because it makes life tricky. So generally, your best bet with faced with something like this is to unwind it, but then you'll see that it is 2 to the n. I think no, you don't. It's 4 to the n. Okay, yeah. Right. And then, so the master theorem doesn't apply to linear expressions like this, but you can actually massage it and actually get the following result. If in the linear form, you just look at whether a is equal to or greater than 1. If it's greater than 1, then all your work is being done in the recursion, so it's just a to the n. And if it's less than 1, then all your work is being done here in the polynomial bit, and so it's just the polynomial plus an extra factor of n lying around. So what do you need to know? So recursive definitions you need to know because, well, they're in the assignment too. I'd say at least one method for solving recurrences. Like if you can't get your head around the master theorem, just know how to do unwinding. Unwinding will always apply. Master theorem won't necessarily always apply, but for the vast majority of cases in this course, almost always the master theorem will suffice. So if you can't get your head around unwinding, get to know the master theorem and its corollary, and then that should probably solve most instances. You need to know how to do algorithmic analysis, right? If I gave, here's an algorithm, give me the running time, right? You need to know, basically that I'm looking for running time in worst case, that the running time is expressed in the parameter n. It's not necessarily the size of the input, but the parameter n. And we're looking for big O generally. We're looking for upper bounds in general. And then, of course, because we covered induction last week, how to do a proof by induction. So last time I talked about how a proof by induction looks. I don't know how to state it. Oh yeah, there we go. Induction proof always should look like this. Always, this is boilerplate code for writing out a proof by induction. Right? So you start with the proposition, the thing you're trying to prove. Right? Often, so in the assignment, for example, I've almost given you that first line, right? I've said, let Pn be this proposition. Right, now this is a proposition. So remember, a proposition is something that's either true or false. But this is a parameterized proposition. This is a proposition that actually depends on what x is. So it's like if x is 1, then it might be true. If x is 2, it might be false. If x is 3, it might be true. So this is a proposition that kind of depends on x. Right, so let Px be the proposition that, and then some thing which is either true or false, depending on what x is. Right, and then we want to show that P of x holds for all x by induction on x. Right, so the idea is that x is some recursively defined object, like the natural numbers, like strings, like trees, like formulas. Right, so we went through a whole bunch of recursively defined structures last week. And I'm going to use that recursive definition to build up my inductive proof. So remember, a recursive definition has two components. It has a base definition and a recursive definition. They may have more than one recursive definition. They may have more than one base condition. And the idea is that we show that P of x holds for all the base conditions. And then the recursive condition, we're defining x in terms of a smaller x, right? So natural number is one more than a smaller natural number. What we do is we assume that the proposition holds on all the smaller instances. And so it holds on this x, and it holds on that x, and it holds on this x. And then my y, which is built up from those x's, I'm going to show that P of y holds because Px holds on all of those smaller instances. Right, so in the case of natural numbers, I'm going to show that because every natural number is either 0 or one more than a natural number. So I show that P of 0 holds. And then I show that if it holds for a natural number n, then it will hold for a natural number which is one more than n. So that's what that's basic induction. Right, so the aim is to show that some property, some proposition holds for all natural numbers. And the way we do that is we show that P of 0 holds, and that if Pk holds, then Pk plus 1 holds. And those two things together with the definition of what a natural number is, tells you that P will hold for all natural numbers. Right? Because P0 holds, P0 holds, so therefore P1 holds. P1 holds, so therefore P2 holds. Right? If I want to know if P123 holds, right, what is 123? 123 is 1 more than 122, which is 1 more than 121, and so on and so forth. I can keep going down, down, down until I get to P of 1, which is 1 more than 0. Now I know P of 0 holds, and so therefore, and then using the inductive case, because P0 holds, it follows that P1 holds, because P1 holds, and so I go back up. So it's I want to know if P123 holds. Use the definition of use the definition of natural number to work out what 123 is, and then I show that P of 0 holds, and then I can slowly build up and show that P of 1 holds for basically, or so P holds for everything up till I get to 123. So a good example to work through to show that these two snippets of code are the same, will produce the same output. I do a proof by induction like this. Right, so I've got, on the one hand, on the left-hand side, I've got the sum of the first n natural numbers, and on the right-hand side, I've got some formula in n. At the end of last lecture, somebody asked how you came up with that formula. So you can do it by experimentation. There's a well-known story about a young, there's a young Gauss, actually. Sorry, I said Euler last week. It's Gauss, who was, I think it was certainly less than 10. I think it was 8 or 5. The teacher was getting a little bit frustrated, so she said, right, add up all the numbers from 1 to 100, thinking that that'll keep him amused for a little bit. And then he sort of like came back 5 seconds later and said, well, the answer is 5,050. And the teacher went, well, how could you work that out? And so went and worked out. And then Gauss said, right, you do this neat little trick. Right, so you sort of say, right, I want to know what the sum from 1 to n is, or from 1 to 100. So 1 plus 2 plus 3 plus, right, plus 99 plus 100. Right, I want to know what that is. Well, this is also, I can count from 100 down. 100 plus 99 plus 98 plus so on and so forth, plus 2 plus 1, right? So those two sums are the same, right? But then, well, if I add them up vertically, I get this is 101 plus 101 plus 101 plus 101, right? And that's just 2s. How many 101s have I got there? I've got 100 101s. I can multiply 101 by 100. So 2s is this. So s is 101 times 50 for 5,050. Right? So instead of sitting there whiling away the time computing up to 100, they get he just sort of end up multiplying a number by 100 and then dividing it by 2, which hopefully most people can do. And so I said, oh, the answer is this. And the same thing works. If this went up to n here, I'm going to get n times n lots of n plus 1 going on there, and that's equal to twice the sum. And you can do this trick with lots of other things. So for example, with the so I'm going to take a simple 1 plus 2 plus 4 plus 8 plus, right, up to 2 to the n. Right, so take that as my sum. I want to know what that is. I keep saying offhand that it's 2 to the n plus 1 minus 1. How do we work that out? Well, if I multiply this by 2, right, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and so on. 2 to the n times 2 is 2 to the n plus 1. Now I subtract one from the other. I subtract this from this, and I get that s is equal to, all right, now everything here cancels except for this guy and this guy, so I get 2 to the n plus 1 minus 1. Right, now that's a trick you can do with finite sums. You can't do it with infinite sums necessarily, so you can't say, for instance, let's look at 1 plus 2 plus 4 plus 8 plus 16 plus, right? So, on to infinity, right? 2s is therefore 2 plus 4 plus 8 plus so on and so forth. So therefore, subtract that one from that one, and I get that s is equal to minus 1. Right? So the sum 1 plus 2 plus 4 plus 8 plus 16 is equal to minus 1 is absurd, right? Because on this side I've got all positive numbers, right? And then here I've got a negative number. You can't do that. Why? Because this is a divergent series, and when things are divergent, they don't behave. You can't just subtract things like this in this way and expect them to behave. So you can't always do that, but in general you can do something like this, right? The sum of the first n powers of 2 is 2 to the n plus 1 minus 1. So that's a way of finding formulas. I can then prove, I want to prove that the sum of 2 to the I goes from 0 to n, is equal to 2 to the n plus 1 minus 1. So an induction proof does away with this dot, dot, dot. Right? I've got this dot, dot, dot going on here. Induction proof basically formalizes the dot, dot, dot. Remember that a proof is a sequence of logical steps where where each step follows from the previous one. If, example, right, so Tn is equal to 2 lots of Tn minus 1. Right, so when I'm unrolling this, right, I'm going to say this is equal to 4 lots of Tn minus 2 is equal to dot, dot, dot is equal to 2 to the I lots of T of n minus I dot, dot, dot is equal to 2 to the n lots of T of 0. Right, so in an unrolling proof, quote, I show that T of n is 2 to the n lots of T of 0 here. But I've got a dot, 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 and this is not really a proof, because this is not a logical sequence of steps. There's some hidden knowledge in there. So this is not a formal proof. So induction does away with the dot, dot, dots. Right, so really, if I wanted to show, so I've got T of n is equal to 2 lots of Tn minus 1. I want to show that T of n is equal to 2 to the n times T of 0. I'm going to prove it by induction. So let Pn be the proposition that T of n is equal to 2n times T of 0. Right, and then I'm going to show that P of n holds for all n in n by induction on n. So I'm going to do this. I'm going to go with this proposition and prove this by induction. Right, going through the steps. So P of n is the proposition that T of n is equal to 2 to the n times T of 0. We'll show that P of n holds for all n in n. Okay, base case. Oh my gosh. Base case is n is equal to 0. Right, so n is equal to 0. So therefore, T of 0 is equal to 1 times T of 0 is equal to 2 to the power 0 times T of 0. Right, so T of 0 is equal to 2 to the 0 times T of 0. So therefore, P of 0 holds. inductive case. Right, so assume P of n holds. Right, so this is how the inductive case stands out. Assume P of n holds. What does that mean? What does that mean? That means that T of n is equal to 2 to the n times T of 0. And I'm going to label that fact, it's called the inductive hypothesis, because I might want to use it later on. Now, what I want to do is I want to show that P of n plus 1 holds. What is P of n plus 1? P of n plus 1 is that T of n plus 1 is equal to 2 to the n plus 1 times T of 0. Right? So, well, let's start by looking at T of n plus 1. T of n plus 1, well, I don't know much about T of n plus 1 other than how it's defined over here. Right? T of n plus 1 is 2 lots of T of n. Okay, now that's fine, I can unravel T of n further, but actually I noticed that my induction hypothesis actually uses T of n. Right, so I could unravel T of n as like 2 lots of Tn minus 2 and so on and so forth. But, sorry, this is 4. But what I'm going to do is I'm actually going to invoke, this is by definition, I'm going to invoke the inductive hypothesis at this point. T of n is 2 to the n lots of T of 0 by the induction hypothesis. Right, so I've replaced T of n by that. And that's really what I want to do, right? I want to make use of this induction hypothesis. This is a fact that I'm assuming holds. I don't necessarily have to. You can actually do induction proofs, or you can get induction proofs where you never use the induction hypothesis. It doesn't make it any less of an induction proof. It just means that you could do it without going through the rigmarole of writing induction. Anyway, this is equal to 2 to the n plus 1 times T of 0. So therefore, P of n plus 1 holds. Right? So assuming Pn holds, we get that Pn plus 1 holds. Right, so Pn implies Pn plus 1. If Pn is true, Pn plus 1 is true. So therefore, by the principle of induction, Pn holds. By principle of induction, Pn holds for all n in n. Right? So that's what I do. I show that P0 holds, and I show that Pn holds, then Pn plus 1 holds. So that's the basic induction, but not all things are as nice as this. And in fact, most things aren't as nice as this. So we need some variations. So sometimes, for instance, I can't show that if Pn holds, then Pn plus 1 holds. Right? Sometimes if Pn holds, I can show that Pn plus 2 holds, but I can't show Pn plus 1 based on Pn. So how do I show? In those cases, how could I show that Pn holds for all natural numbers? So if Pn holds, then Pn plus 2 holds. So I can try my inductive case and I like bash around, and I just can't resolve it. But what I can do quite easily is show that if Pn holds, then Pn plus 2 holds. Right? An example would be that n squared mod 4 is equal to 0 or 1. Right? So if n squared mod 4 is equal to 0, then n plus 2 squared is equal to n squared plus 4n plus 4. So n plus 2 all squared mod 4 is equal to just n squared mod 4. Right? So if n holds, so if this is my proposition, P of n is the proposition that this thing here. So if P of n, sorry, this is my proposition here. P of n is the proposition that n squared mod 4 is 0 or 1. So that was irrelevant. n plus 2 squared mod 4 is equal to n squared mod 4. So if n squared mod 4 is 0 or 1, then n plus 2 squared is 0 or 1. So if Pn holds, Pn plus 2 holds. Right? Nice, simple proof that Pn holds, then Pn plus 2 holds. Going from Pn holding to Pn plus 1 holding is not so clear cut. Right? You have to sort of break it up into cases. Like if n squared mod 4 is 0, then it becomes 1, and if it's 1, then it becomes 0. But what I can do a nice little trick, right? If n holds and n plus 2 holds, right, I can show that P0 holds. Let's say P0 holds, then P2 holds, then P4 holds, then P6 holds, right? So I've now shown if P0 holds, then all the even numbers hold. And if I show that P1 holds, then I can show all the odd numbers hold. Right? So I've got a very simple proof. Pn implies Pn plus 2, but to get it for all the integers, I can say, right, it holds at 0 and it holds at 1, and every natural number is 2 more than an odd number or 2 more than an even number, and so on and so forth, down to 0 or 1. Right, so if I show P0 holds and P1 holds and Pn implies Pn plus 2 holds, then that gives me all of n. Right? So that's an example of a variation. A simpler variation. So that was the case of induction steps greater than 1. Right? So my inductive step went from n to n plus 2 rather than n to n plus 1. So induction step greater than 1. A simpler variation is maybe it doesn't hold for all n, but maybe it holds for like n greater than 4 or something like this. So my base case, I don't want to be 0 because it doesn't hold at 0, it doesn't hold at 1, doesn't hold at 2, but it holds at 3, and if it holds at n, then it holds at n plus 1. Right, so that's induction from m upwards. Right, so the base case is that P of m holds, and the inductive step is that if k is greater than or equal to m, and P of k holds, then P of k plus 1 holds. Right, and then the conclusion is not that P of n holds for all natural numbers, it's that P of n holds for all natural numbers greater than or equal to m. Here's an example, right? For all n greater than or equal to 1, the number a to the n minus 2 to the n is divisible by 6. Now this is certainly true for n equals 0 as well. But this is a case where it's like, okay, I don't want to do the case n equals 0. Maybe I could say a variation. The number a to the n minus 1 minus 2 to the n minus 1 is divisible by 6, because that's not true for n equals 0. I think, no. Right, and so my base case is now take the case n equal 1, and my inductive case, if k is greater than or equal to 1, then I show that if this is true, then this is true. And I leave the proof as an exercise, but the hint there is to rewrite 8 to the k plus 1 as 8 lots of 8 to the k minus 2 to the k plus 2 to the k. Right? So this is 8 lots of 8 to the k plus 0, if you like. But the point is that this 8 to the k minus 2 to the k is part of my inductive hypothesis. My inductive hypothesis says that if this bit here is divisible by 6, the inductive hypothesis is that this thing here is divisible by 6. An alternative is to do induction steps greater than 1. We saw an example there. Right? So I show that P of k implies P of k plus L rather than P of k plus 1. Then the conclusion, if I only show that P of m holds, the conclusion is that P of n holds for every nth natural number greater than or equal to m. And of course, I can then use that to say, right, so here I said, in my previous example, I showed that P of n implies P of n plus 2, and P of 0 holds. So therefore, P holds for every second number from 0 onwards, i.e. it holds for every even number. But then I also showed that P of 1 holds, and so therefore P holds for every second number from 1 onwards, which means it holds for every odd number. Right? So now those two cases give me a chance to cover all of the natural numbers. And in fact, nope, that's not the example. The given example is that every fourth Fibonacci number is divisible by 3. So let's go through that proof. So, right, so what's the proposition? Proposition is that, well, this is P of n. Okay. What do I want to show? I want to show every fourth. So I want to show that every fourth Fibonacci number is divisible by 4. So every fourth, if n is a multiple of 4, then 4 divides the nth Fibonacci number. Right? So I want to show that P of n holds for every fourth value n. Right? So remember that f of n, f of 0 is equal to 0, f of 1 is equal to 1, f of 2 is equal to 1, f of 3 is equal to 2. Sorry, divisible by 3. F of 4 is equal to 3, because 3 is not divisible by 4. Right, so I can see it holds at it holds at 0, it holds at 4. If I carry on, right, 21 is divisible by 3, but these intermediates are not necessarily divisible by 3. Right, so the fact the Fibonacci number being divisible by 3 is something we witness every fourth one. We might witness it some other times, but I'm going to show that this is true. This is not just a coincidence. It's true forevermore. So if 4 divides n, then 3 divides Fibonacci of n. And this is related to the. This is somewhat related to the challenge question, right? The challenge question asks you to find. Well, basically, the bonus question is to show that you will always repeat. You always get a point where your Fibonacci numbers will repeat when you're looking modulo, in this case modulo 4 or modulo 3. So if I look modulo 3, right, the Fibonacci numbers will go back to 0 infinitely often, right, and regularly. Right, so they go back to 3 every fourth turn. Right. Anyway, so how do I do this? Right. So P of 0. So proof by induction. On n, and what I'm going to show is I'm going to show that P of 0 holds, and that if P of n holds, P of n plus 4 holds. Right. So P of 0 is that f of 0, which is 0. And 0 divides f of 0 divides 0, so therefore 0 divides f of 0, so therefore P of 0 holds. Sorry? Oh, so that one starts at 4. Well, I start at 0. If you like, I can do P of 4 as well. Right? There's no limit to how many base cases you can do, but you do need to make sure that you do enough base cases so that your recursive case is not messed up, right? Because what do I want to do? Can I give an example? I'll come back with an example. That's P of 4, f of 4 is equal to 3. 3 divides 3, so therefore 3 divides f of 4. So therefore P of 4 holds. Now, I could carry on. I could do P of 4, I could do P of 8, I could show P of 8 holds, I could show P of 12 holds, but that still doesn't show that P of n holds every time n is a multiple of 4. So I need to now show that I want to show induction step. I want to show that if P of n holds, then P of n plus 4 holds. Okay, so what do? We assume P of n holds, i.e. 3 divides f of n. Now I want to show that 3 divides f of n plus 4. So, well, what is f of n plus 4? I don't know much about f of n plus 4, other than it is equal to f of n plus 3 plus f of n plus 2. Well, what is f of n plus 3? F of n plus 3 is f of n plus 2 plus f of n plus 1. And I already had an f of n plus 2 there, so it's that. What is, keep going, f of n plus 2. F of n plus 2 is f of n plus 1 plus f of n. And I already have an f of n plus 1, and I had 2 f of n of those, so I get 3 of those and 2 of those. Okay, but I'm going to stop at this point. Right, why? Because 3 divides f of n, and 3 divides 3 lots of f of n plus 1. Right, so 3 divides 3 lots of f of n plus 1, because 3 lots of f of n plus 1 is a multiple of 3. And 3 divides 2 lots of f of n because, well, 3 divides f of n. So therefore, 3 divides 3 fn plus 1 plus 2 fn, which is equal to fn plus 4. Right? So assuming Pn holds, it follows that Pn plus 4 holds. So by the principle of induction, P of n holds for every fourth n from, well, I've proved that P of 0 held. So P of 0 holds, so therefore P of 4 holds, therefore P of 8 holds, therefore P of 12 holds. So now I've shown it for infinitely many P, with all with finite steps. Sometimes, so the thing to note about with induction, right, you show P of 0 holds, and then you show that if pk holds, pk plus 1 holds. So P of 0 holds, so therefore P of 1 holds. P of 1 holds, therefore P of 2 holds. Right? But to get to 2, I only looked back at 1. Right? So P of 2 held because P of 1 held. But P of 0 also held. So sometimes it can be useful to not just know that the next one down held, but basically the next one down and all of the ones leading up to that point held. Right? So P of 0 holds and P of 1 holds, and from those two things I can deduce that P of... thank you, reminded me. If you get too hot, remind me. I can turn the air conditioning on. I've worked out how. Right. So you can deduce that P of 2 holds because of P of 1 and because of P of 0. Right. And likewise, I might be able to deduce that P of m holds because P of n holds for all smaller n. Right. And if we think back to how the natural numbers are defined, right, if they hold at the previous step, that means that they must hold at all the steps earlier than that. And so sometimes this stronger hypothesis, right? So you need to you don't just assume that pk holds to get to pk plus 1, but you assume that pk and a bunch of smaller things also hold to get to pk plus 1. Then you can still get the conclusion that P of n holds for all natural numbers, or for all natural numbers larger than the base case. Right? So this is why it's called strong induction, because you've got a stronger inductive hypothesis. Right? So in the basic induction, the induction hypothesis is just pk. Right? Now I've got pk and pk minus 1 and pk minus 2. Right? I've got a whole lot of things. A good example where this applies is when you look at say, writing a number of product of primes. Because just because n can be written as a product of primes, it's not immediately obvious that n plus 1 can be written as a product of primes. Right? So the way it works, right? So I'm looking at my inductive case, right? I assume that all x between 2 and k can be written as a product of primes, and I want to show that k plus 1 can be written as a product of primes. Well, there are two cases. K plus 1 is prime itself, in which case it's written as a product of primes, just write it as itself. Or k plus 1 is the product of two smaller things, right? An x and a y, where x and y are both smaller than k plus 1, i.e. x and y are somewhere between 2 and k. So x and y can be, by the inductive hypothesis, x and y can be written as product of primes, and so therefore x times y is a large product of primes, and so therefore k plus 1 can be written as a product of primes. Right, so I never used the fact that because k can be written as a product of primes, k plus 1 can be. What I used was the fact that every number smaller than k can be written as a product of primes. Some other examples. So this should, in terms of assessment, you don't need to know, if I said, I'm never going to say prove this by every fourth step or whatever. These are just ways of massaging basic induction into a form that might be suitable. Right? So in general, induction goes up. Right? You start at 0 and you go up. But there's nothing stopping you starting at 0 and going down, right? The only difference is that you start at 0 and go down. You don't show that P of n implies P of n plus 1. You show that P of n implies P of n minus 1, right? There's 0 to get to minus 1. I've got to subtract 1. To get to minus 2, I've got to subtract 1 again. So negative numbers can be included. I can go backwards. That's called backward induction. So if P of n, then P of n minus 1. Right? If you start with P of 0, then by backward induction, you can get all the negative numbers. You can also start at a negative number. Right? The base case might be like minus 1,000, minus 1,000,000, like that, and then you just go up from there. And so those two examples, in order to reason about all of the integers, right, so I want to prove something's true for all the integers, you have to prove it's true for all the integers, there's no starting point of the integers. You can't sort of say, well, we're going to start here and go up. And so what you have to do is you have to start at some point, go up, and then start at that same point and go down. So you have to do sort of two-directional proof. Right, so it's two separate induction proofs, one for the positive natural numbers and one for the negative natural numbers, one for the base case. And this is based on the idea of well-foundedness. So when we talked about the well-founded operation, basically you can do induction on any well-founded set. You start with the least element and then you go up. The integers themselves with the normal ordering relation are not well-founded. If you do this funky ordering where you sort of like all the positive numbers are less than all the negative numbers, then that is a well-founded set. And that's exactly what you're doing. You're doing induction on the positive numbers and then induction on the negative numbers. the other one, the other very strange one that is actually, we use it implicitly all the time, particularly when we're doing algorithmic analysis. And it's here, you don't need to know exactly what's going on, but you need to understand the principle why we can make simplifying assumptions when we're doing algorithmic analysis. So the classic example is with algorithmic with analysis is you have something like t of n is equal to 2 lots of t of n over 2 plus say n, right? And then we're trying to solve this using unrolling, right? This is 4 lots of Tn over 4 plus n plus plus 2 lots of n over 2, right? Equals dot dot dot. The ith term I lots of n going on there. The ith term looks like this, and then dot 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 is equal to 2 to the n times t of 0 plus n log n. So 2 to the log n. Times t of 0 plus n log n. Now, these equality only hold, of course, when n is a power of 2. We can keep doing those divide by 2's. What happens when n is not a power of 2? Really, what we're looking at is, say, maybe something like ceiling of n over 2 there. And it might not behave, the ceiling function doesn't behave as nicely as, say, n over 2, right? It's like you don't get log n, but you get something like ceiling of log n, right? And doesn't behave quite as nice. Forward-backward induction basically tells you that it's really just sufficient to consider powers of 2. You don't need to worry about, you know, the edge cases, more or less. So what you do is you prove it's true for n equal to 1, n equal to 2, n equal to 4, n equal to 8, n equal to 16. So you have these gaps. You prove it's true for the easy cases, and then you backfill the gaps. Right? So you show it's true for a particular example. You show it's true for 1, 2, 4, 8, 16, 32, and then you show, right, I need to show it's true. If it's true for 4 and true for 2, then I can go back and fill in it's true for 3 and 2 and 1, right? Or so 8 and 4, it's true for 8, it's true for 7, it's true for 6, it's true for... So once I've shown it's true for 8, I backfill in the missing ones to prove that it's true for all n. Do I have an example? No, I don't have an example in this particular case. But that's basically the intuition behind forward-backward induction. Basically, it just says it's okay to assume, particularly when it comes to algorithmic analysis, that n is a power of 2, and we'll just fill in the gaps appropriately if needed. So you don't need to know how to do forward-backward induction. It's just there for completeness. For this course, it's there for completeness. So you can understand why this hand-wavy algorithmic analysis is actually sound. You could actually make it more sound with some forward-backward induction proofs. Right? This is what you would use to fill in the blanks. That brings me to the final topic on induction, which is I think is the most important one for computer scientists, because structural induction is something that is very fundamental to, because recursive data types are so prevalent in computer science, structural induction is very useful for proving things about recursive data types. And so it's something that you see fairly early on in computer science. You don't see it very much in mathematics. So this is like another thing that we know, or we tend to teach a lot earlier on than mathematicians. We understand it, tend to get more familiar with it a little bit earlier on. So the idea is that, so induction applies over any recursive data type. You just have your base cases and your inductive cases. There's nothing special about doing induction over the natural numbers. Natural numbers are just some some structure, right? We have a natural number is the 0 or one more than a natural number, right? We build it up like that. The same principle applies for just general recursive data types. And so what you do is you show that it's true for all the base cases, all the minimum cases, and then you show that if it's true for all the smaller cases, it's true for any case that you can build up from that. Right? So, as an example, right, remember that a word is either the empty word or it's a letter followed by a smaller word. So to prove that a property holds for all words, what you would do is show that the property holds for the empty word. And if the property holds for a word, then you can put any letter on the front of it and the property will still hold. Right? So, as an example, right, so I'm going to take the formal definition of concatenation, the formal definition of length. These were based on the formal definition of what a word is. So a word is either the empty word or a symbol followed by a smaller word. Right? The concatenation is defined as follows. Lambda concatenated with v is just v, and AW concatenated with v is A followed by W concatenated with v. Length of lambda is 0, length of AW is 1 plus the length of W. So these formal definitions of these functions, they can also be thought of as programs. Right? Here is a program that computes the length of a word. Right? If the word is the empty word, return 0. If the word is of the form AW, return 1 plus recursive call to the length of W. Right? Same thing with concatenation here, but concatenation takes two words and returns a word. Right? So if W is equal to the empty word, return V. If W is not equal to the empty word, it's equal to a symbol followed by a smaller word. Concatenate W with V and stick A at the front of that. Right? So these are functions, but they're also programs. There's got this connection between functions and recursive functions and recursive programs. And that's something you see in the assignment as well. Right, so you define a tree, I'm asking you for functions, but really those functions are just programs for computing it. If you define your tree data type in whatever language you like, as long as it matches the abstract form, then your programs, you can write a recursive program very similar to the way you would define the functions. Anyway, here's my definition of length and concat, and now I want to prove that for all words W and all words V, the length of WV is equal to the length of W plus the length of V. Right? That seems obvious to the face of it, right? WV is just W tacked onto V, so the length, the number of symbols in WV is equal to the number of symbols in W plus the number of symbols in V. But how do I prove that for all words? Right? Intuitively, that seems right, and if you were to write it down, you would sort of like, let W be A1, A2, dot, 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 AN, right? So length of W is equal to N, and then V is equal to, B1, B2, dot, 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 BM. So length of V is equal to M. So WV is then equal to A1, A2, dot, 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 AN, B1, B2, dot, 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 BM. So the length of that thing is N plus M. The thing is, the proof, the intuitive proof, has these dot, dot, dots in it. How do I formalize the proof to get rid of the dot, dot, dots? Well, I say, right, let PW be the proposition that for all words V, right, so I'm just taking I'm just doing a proposition based on W. Right, so for all words V, the length of WV is equal to the length of W plus the length of V. And I'm going to show that P of W holds for all W in sigma star by structural induction on W. Right? Exactly the same format as we described for proof by induction. Right? Let PW be the proposition that we'll show that PW holds for all blah by, in this case I'm going to say structural induction on W, because W is not a natural number, it's a structure. Proof. Base case, right? Exactly the same layout. Base case, W is equal to lambda. So, right, how do I do this? So base case, so I want to prove that P of lambda holds. So P of lambda is that length of lambda W is equal to length of lambda plus length of V. So length of lambda V is equal to length of W plus length of V. Right, so let's start with the length of WV. And actually, we just go back, pick up this, and to freeze that. Right. So length of lambda V. Right. Well, I don't know what the length of lambda V is, but I do know what lambda V is, right? Lambda V, by the definition of concat, is equal to V. Right? That's good. Okay. It's a good start. What do I want to get to? I want to get to the length of lambda plus the length of V. Well, I've got the length of V. What's the length of lambda? Well, if I look up there, the length of lambda is 0. So I need to throw in a 0 somewhere. Well, length of V is equal to 0 plus the length of V by straight up arithmetic. And then by the definition of length, 0 is equal to the length of W, is equal to the length of lambda, right? So this is just a case of going back through the definitions and just unwrapping everything, right? Length of lambda V is equal to this, is equal to this, is equal to this. Right? And now so therefore P of lambda holds. Right? I've shown that this is, if you take the top left and the bottom right, that together is the proposition P lambda. So P lambda holds. Okay, inductive case. So I assume that W, so how is W constructed? W is either the empty word, which I've covered, or W is of the form AW prime, where W prime is a smaller word. Now the inductive hypothesis is that P of W prime holds, right? So P of W prime, so P holds for the smaller word W prime. Right? So W is equal to AW prime and P of W prime holds. So in other words, that is, for all words, what is PW prime? PW prime is the statement that the length of W prime V is equal to the length of W prime plus the length of V. Right, so I want to show that P of AW prime holds now. So let's start with the length of AW prime V. What is that? Well, I don't know what the length of AW prime is, AW prime V is, but I do know how to compute AW prime V. If I look at my definition of concat, right, AW prime V is equal to A of W prime V. A W prime V. Now I can use my length function, right? Because this here, my definition of my length function doesn't know how to cope with this, but it does know how to cope with something like this, right? This is length of a symbol followed by a word, right? If I look at my inductive definition of length, symbol followed by a word is just, well, that's just 1 plus the length of the word, right? Now, this thing here is up here. I know what this thing here is. Right? My inductive hypothesis tells me what that is. This is this, right? So that's that by the inductive hypothesis. So I'm getting closer, right? What am I trying to aim for? I'm trying to get the length of AW prime plus the length of V, right? Well, okay, so now what? Well, this bit here, 1 plus the length of W prime, that's just, right, 1 plus the length of W prime is equal to the length of AW prime, right? It's the second length rule in reverse, going that way. Right, so this thing here is equal to this thing here by in the inductive case, the recursive case of length. And I'm done. Right, that's P of AW prime. Right? So I've shown that if PW prime holds, then PAW prime holds for any symbol A. Right? And every word is either the empty word or it's a symbol followed by a smaller word. So we have P of lambda, and we have for any word W prime, if P of W prime holds and P of AW prime holds, hence P of W holds for all W in sigma star. So I've shown that all... Where have we gone? Oh, that's the last one. Oh no. Skipped a few. So for all words, W, P of W holds. P of W being the proposition that length of WV is equal to length of W plus length of V. So this intuitive notion of length that we understand, you concatenate, or the interaction between concatenation and length, intuitive notion, we concatenate two things, then it's the length of the concatenation is the sum of the lengths. Right, we've now proven holds for all finite words. Second example, right? Remember, we defined the append function, which basically does things the other way around, right? So append takes a word and a symbol and sticks the symbol at the end of the word. Right? So if the word is the empty word, then append lambda x is just the word x. If the word is the form AW, then the word is A followed by the result of appending W to X. So X to W. Right? Now what I want to show is that the interaction between concatenation and append, right? The append of a concatenation is equal to the concatenation of the append. Right? So that of course makes sense, right? If I stick X on the end of the word WV, that's the same as sticking X on the end of V and sticking that on the end of W, right? It seems to make sense. How do we prove it? We prove it by induction on W. Right? So let P of W be the proposition that PW be the proposition that for all V in sigma star and all X in sigma, append WV X is equal to W append Vx. Right? Then how do we prove it? Okay, we'll prove holds. We will prove P of W holds for all W in sigma star by induction on W. Right? Standard format. How it all lays out. Let P of W be the proposition this. We'll prove it holds this by induction on that. Base case. Right? The base case is that W is the empty word. What have we got? Well, append WVX is equal to append, right, this is just lambda Vx. Right? I don't know how to do append lambda Vx, but I do know how to do lambda V. Right? Lambda V is equal to V by concatenation, by the base case of concatenation. That append Vx is equal to lambda concatenated with append Vx by the base case of concat. Right? And so therefore, which is equal to W append Vx. So therefore, P of lambda holds. Right, inductive case. Right, so let W be AW prime and assume P of W prime holds. That is, that for all V in sigma star, for all X in sigma, we have append W prime Vx is equal to W prime append Vx. Now we're going to show that P of W holds, or P of AW prime holds. Right, so append WVx is equal to append AW prime Vx, right, which is equal to, so that's just the definition of W, append A of W prime Vx, that's the definition of concat, the inductive definition of a cat. Now we have the recursive definition of append. Right, append A W prime V is equal to A followed by append W prime Vx. Right, so that's the recursive definition of append. And this thing here is my induction hypothesis. So this thing here is equal to A W prime append Vx by the inductive hypothesis, which by commutativity of concat or whatever, this is A W prime append Vx, we're running out of space, which is just W append Vx. Right, so therefore, P of W prime implies P of W. Right, and so by the principle of induction, P of W holds for all W in sigma star. Done. Right? So, interaction between append and concat is kind of as you'd expect. And then, oh, there we go. There is the proof. And then, finally, is an example that I'm going to leave to do the work. I'm going to define the reverse function in terms of the append function and leave it as an example to show that reverse of how reverse and concat, reverse of the concatenation of W and V is equal to the concatenation of reverse of V and reverse of W. So that, and then finally that exercise there to practice your base induction. Yep.
I did not, the first quiz question, I did not understand why the inner loop is not n. Like, why is it not ON square instead of ON? Is it because in the inner while loop we are not comparing to n? Or
yeah, I mean, if you just look at where, like, every time you execute, I mean, if I goes down to
I is going up, j is going down.
Yeah, so I is going up. If I goes all the way to the top, j doesn't go down any further, right? Because it's like basically I is going to go up to where